Hey, Silas. All right, let's finish up this day here. It's been a long one. I feel like my 6th session today.
Oh, man.
Yeah. All right, but that's okay. I got most of tomorrow off and most of next week off, so got a little vacation coming up here, probably just like you. Are you off all next week or just Thursday and Friday?
All next week.
All next week, so I assume we won't be having any sessions next week?
I don't think so.
Okay. So let's make this one a good one. Which section are we on?
Still on 6.5.
Okay.
We're doing the second part of it.
All right. Let's see. These go down. Tell me where to stop.
It's like a rational root theorem, an imaginary root theorem.
Okay, this talks about irrational roots coming in pairs also. I think we talked yesterday about imaginary roots always come in pairs, and so do irrational roots, like 2 plus root 7. That's an irrational answer. It's real, but it's irrational. Therefore, if I have an equation like this, that necessarily must have a rational root, right? Because we know there's 3 solutions. Well, they can't all be imaginary and irrational. There could be 2 imaginary, but there cannot be 2 imaginary and 2 irrational. That would be 4 solutions. So since it's an odd number of solutions, one of them has to be rational, which is one thing that's helpful because we have a rational root theorem that tells us that if there is a rational solution, its numerator is a factor of 10 and its denominator is a factor of 1. And here's saying the same thing with imaginary roots. If a plus bi is a root, then a minus bi is also a root. Excuse me. Wow. I'm not sure if that's a cold or allergies. I just left a student who had a cold. I hope I didn't get it that quick. I don't think you can catch a cold that quick. All right. Is this the section you started covering today?
Yeah.
Writing a polynomial from its roots?
Yep.
Okay. So this one is saying that I and 2i are roots. So how many roots are there?
4.
Correct. What are they?
I, 2i, negative 2i.
So what are my linear factors? In other words, in order to come up with a polynomial, I got to multiply together 4 factors. What are they? In other words, we found the roots. Now let's write the roots as factors.
The x minus I, x plus I.
And
then x minus 2i, x plus 2i.
okay. Now what we're going to find out when we multiply these together is that the i's disappear, and we'll come up with a polynomial that does not have any i's in it. So what are we going to get when we multiply those two together?
X squared plus or minus 1.
Well, you're close.
No.
It's x squared. It's difference of squares, so it would be x squared minus I squared, right? But what is I squared?
Negative 1.
So x squared minus I squared is actually x plus 1. Okay? And what do we get when we multiply these two together? That's also difference of squares.
The x squared minus 4i.
Which would 4i squared.
4i squared.
Right, which turns into
negative 4.
okay, we're going to have x squared minus 4i squared. I squared is always minus 1.
Okay.
So it's x squared plus 4. Multiply these two together, foiling them.
Get x to the 4th plus 4x squared plus x squared plus 4.
Which is x to the 4th plus 5x squared plus 4. And notice something about this. It happens to be a quadratic in disguise, so we could solve this by using substitution, right? It's going to be x squared plus 4 times x squared plus 1. Oh, excuse me. Sorry. We just did solve it. In other words, we just came from that, so we don't have to factor this.
Okay.
But do notice that if you gave me this and it was not easily factorable by using substitution, I would have a terribly difficult time solving this. In fact, make this a 3, and now try to solve that. Notice, first of all, that the rational root theorem isn't going to do me much good. We already know that there are no rational roots to this. So I can experiment all day with my P over Q, and I'm not going to come up with a solution. I also don't know how to find the imaginary roots of it. So when you have quartic or 6th degree polynomials, you can never be sure that you have a rational root. It's only if you have odd degree polynomials like cubics where you are guaranteed to have a rational root, and you can therefore use the rational root theorem to come up with it. And once you have one root on a cubic, well, if you divide by that root, you're left with a quadratic, and you know how to factor quadratic. So cubics are actually not that difficult to do, because you know there is one, at least one rational root. There might be 3, but there's at least one. Whereas when we get into quartics, then it's tough, because you don't know for sure. There may be 2 complex roots, there may be 4 complex roots, there may be 2 complex and 2 irrational roots. And we don't have a way of finding the irrational or the complex roots, at least not that I've ever been taught. Some guy in the 16th century, Bombelli, came up with a way, but it's called the, it involves roots of roots. In other words, you end up with answers that look like this. And I don't know how to do that. So, all right. So let's do number 2.
Okay.
I guess, let's see, what comes after this? I don't want to skip this right away. That's it. Okay. So let's do number 2 since this is the
And
last. Okay,
also
so here's my solutions. What else do I have as a solution?
positive 4 and negative 4i.
Yeah, in other words, they gave us the positive 4, so we know that that's also a solution. So it appears I have 3 solutions. So what are my 3 factors?
What? I'm confused now.
Okay, we know we have 3 solutions. There's one of them.
What
That's a real solution, so it doesn't necessarily come in pairs.
Okay.
Okay, and they told us that 4i was a solution. Well, we know imaginary solutions must come in pairs, so we must have minus 4i also. Notice this is not the same as the first one. The first one had 2 imaginary solutions, so we knew there were 2 others, the conjugates of these. This one, they're giving us 1 real and 1 imaginary. So what's the real linear factor?
X minus 4.
X minus a minus 4.
So x plus 4?
Yeah. If I gave you 3 factors and I said they were equal to 0 and I said solve it, you would take this and set it equal to 0. X plus 4 equals 0, meaning x equals minus 4. So when they give you this, to work backwards, you have to take x minus this number. And that gives you x plus 4. And what are the other 2?
X plus 4i, x minus 4i.
Let's multiply those 2 together first because we know the i's are going to go away.
Then x squared plus x squared minus 16i squared. So x squared plus 16.
Good.
And then you
Now multiply that times that.
X to the third plus 16x plus 4x squared plus 64.
Math seems to be getting better. Or have you always been good at doing that?
It's just simple.
Yeah, I know.
For now.
But even still, that's pretty good. I got a lot of students that would have to pull out a calculator to do what you just did. So here's our polynomial. If I started with this polynomial and using the P over Q rule, in other words, the first thing I would do would look for a rational solution, I would find that x equal minus 4 is one of them. I would have to look at all the factors of 64, though. So I would be looking at 64, 1, 32, 2, 16, 4, 8, and 8, plus or minus on each one. So if they gave me this polynomial and they said solve it, this would be my first step. I got 1, 2, 3, 4, 5, 6, 7 times 2. I got 14 possible solutions. As I use synthetic division on each one, only one of them is going to work, and that's the minus 4. Because we know that, because they told us that minus 4 was a solution. Okay? So as all we're doing here is going backwards of what we did yesterday. Only it's not as hard because we don't have to use the P over Q. So all we have to do is come up with the polynomial. and they gave us all the hard stuff. In other words, they told us that x equal minus 4 is one solution. And they even gave us one of the imaginary solutions. So they made it really easy. Okay, you have any questions about any of that, of what we're doing here?
Not yet.
Okay, let's try a third one. Have you done all three of these in class?
I think we did 2 of them.
All right, let's try the other one. So here we have solution of minus 2 and 3i. You take it from here.
Yeah.
So that's another solution. Now write the roots as factors.
The x minus 2.
No?
X plus 2.
Right.
X plus 3i. X minus 3i. And you
Add those two first, or multiply those two first.
have x squared minus not plus 9.
Good.
Then x to the third plus 9x plus 2x squared plus 18.
There's your polynomial. It satisfies those conditions. If you put that polynomial into your calculator and figure out the zeros, you're only going to get one of them, at minus 2. Why is that? Because the zeros of a polynomial only cross the x-axis with the real solutions, not the imaginary ones. That noise is my dog going crazy. Sorry. X raised to the third plus 2x raised to the second plus 9x plus 18. Notice it only crosses the x-axis one time. And this even gives us the roots. Minus 2, minus 3i, plus 3i. This is a nifty program. It gives us all kinds of things. It gives us the derivative, gives us the integral, geometric series, all of it. All right. Well, it feels like you know this stuff pretty good. Do you have any questions?
No.
Yeah, let's give you a Thanksgiving gift and let you go 10 minutes early. Unless you have specific stuff you want to go over.
The other thing we did was fundamental theorem of algebra.
Okay.
That's the next lesson.
Let me look at that, what they have over here. That's this one here.
The teacher kind of blew through it last minute, so.
Yeah, I imagine. Okay. Okay, the degree of the exponent indicates how many possible solutions there are. We've been talking about that. If it's a cubic, there's 3 solutions. If it's a quadratic, there's 2 solutions. Now, it's not to say that there's 2 separate solutions. In other words, if I have a quadratic that is like this, Well, that quadratic is x squared minus 2x plus 1. That has two solutions. It just so happens that they're both the same. So this would have a solution x equal 1, but it would have multiplicity of 2 on it, is the way you talk about that. We say that if something has two solutions that are the same, then it has one solution with multiplicity of 2. Or if it's x minus 1 times x minus 1 times x minus 1, then it would have multiplicity of 3. Okay? The number of times the graph crosses the x-axis will determine the number of real solutions. We just talked about that also. If it only crosses it one time, there's only one real solution. If it crosses it 3 times, there are 3 real solutions. Use a combination of all of the methods to find the solutions. Well, we know how to do that. Let's look at this top one here. Just tell me how we're going to solve that. What technique are we going to use? It's a quartic, so it could be hard. There better be an easy way to solve it, otherwise we're going to be stuck.
Factor it? No.
Yeah? No, you're right, but how can we factor it?
The x squared minus 11, x squared minus 1.
Good. What you basically just did was substitution. You let u equal x squared, and you turned it into u minus 11 times u minus 1. You don't actually have to use the substitution if you can do it, and you can, so there's no reason to even list the u substitution. So now let's solve it. It's the next thing I can write.
Not sure.
Well, if two things multiplied together equals 0, what does that mean? One of them has to be 0. You can't multiply two numbers together and get 0 unless one of them is 0. For that matter, you can't multiply 3 numbers together and get 0 unless one of them is 0. Or any number, any string of numbers. So it means I can set that equal to 0 and solve, or I can set that equal to 0 and solve. So let's do the first one.
X squared equals 11. Root 11.
What's the other one?
X squared equals 1. X equals 1.
So what's wrong with this?
Is there a solution?
We only have 2 solutions. But it's a quartic. We need 4 solutions. Where did we lose them? We made a mistake. There you go. Now we have 4 solutions. We can do that one in the same manner.
Okay.
I don't know if it'll factor nicely, but we're going to use substitution. Let's see if it factors nicely. 5x plus something, 5x squared times x squared. And let's see, what do we need? We need opposite signs. And let's see, 4 and 2, that's not going to work. 4 and 2 I don't think work in any combination. 1 and 8. 8 and 1. That doesn't work either. We can't factor this easily. So on this one, we're going to have to use U substitution to really get a handle on it. What's my U equal? It's always that middle term without the coefficient.
X.
X squared. X squared is the middle term. Okay, so how am I going to write this first term based on that?
Factor x squared out of it?
Well, no. If U is equal to x squared, then U squared is equal to x to the fourth, right?
Yeah.
So what I'm trying to do is write that as a quadratic in U. So the first term is 5U squared.
Okay.
What's the next term?
Plus U.
Minus 8. Now, why was I forced to use substitution? Because the only way I can solve this is using the quadratic formula. So let's use it. What is U equal to?
U equals plus or minus.
No, it's minus B.
So
In other words, we're using the quadratic formula on it.
So we just have negative 1.
Okay? Now plus or minus.
Square root of, just be 1 again. Minus 100, no, it would be plus 160.
So let's simplify that. Yeah, let's see. That's
1.
minus 1/10 plus or minus, no, I don't think 161, anything divides into it.
No.
So there's our answer for U. So, well, this is a good one. So now we have to plug this in to our substitution. U, remember, is equal to x squared. So if U equals x squared, solve that for x.
Is it?
What's the first thing I'm going to write?
X equals
What's the next thing I'm going to write?
root sign.
No, plus or minus.
Plus or minus.
In other words, whenever you take the square root of an equation, the first thing you want to write is plus or minus on the other side. And now, before we try to figure out how to do this, let's just do this. Let's put the radical sign and put 1/10 in there, plus or minus root 161 over 10. How many answers do we have?
2.
4.
4.
See why? Here's one answer.
Because we have
A plus end to that. So one answer is minus 1/10 plus root 161 over 10. Another answer is minus that same quantity. That covers the plus or minus there. Third answer, plus the radical. Now we use the minus sign inside. And finally, the fourth answer is x equals minus the root of this whole thing. And for this problem, I would imagine they would accept this answer rather than having to go in, excuse me, did I do that right? Yeah. Rather than to go in there and try to simplify that answer. Let's see. This is a positive number inside the radical. So this is going to produce real roots. This is a positive number. In other words, the square root of 160. Well, maybe it isn't. Oh, yes, it is, because this is just 1/10. That's going to be at least a number greater than 1. So these two are going to give you real answers. These two are going to have negative numbers inside the radical sign. These are going to give you answers with I in them. Now, how to turn that into something that has I in it? I guess you would just convert that to... That's a good question. I'm not sure. I guess we would have to convert this to a number. Not that hard to do. You could put this in your calculator and come up with a number, a decimal number, and then take the square root of that negative number, and then convert that to I. So this was actually a good problem. I have not seen a problem of this nature where you had to use U substitution and then you had to use the quadratic formula to solve the quadratic in U. And then once you solve the quadratic in U, solving for x gives you really messy looking answers like that, where you have a radical sign inside of a radical sign. That's the way they used to do it 400 years ago. Bombelli. I'm looking at a poster right now, and he's got his equations, and they've got radical signs inside radical signs. In some cases, the inside radical is a negative number. So that's probably how they did that. Now that I think about it, the radical solution is probably using substitution to do it. Now, number 3, we're going to have to use the rational factor theorem. There's no other way to do number 3. We can't use substitution. Notice that we can't put that into a quadratic in U. We could let U be x squared, but then that doesn't become U squared, so it doesn't become a quadratic. So the only way to solve number 3 is we know that there is at least one rational factor. Let's figure out what it is by substituting all the possibilities. Once we get that number, we'll know what the remaining quadratic is. And then we can use the quadratic formula, if necessary, on that to come up with all 3 solutions.
Yeah, we did that one in class.
Okay. The toughest one here really was number 2.
Yeah, we did that one.
In terms of the most work involved and the most complicated looking answer involved. All right. I will probably speak to you a week from Monday, I would assume, if you guys start back up on Monday, Tuesday, and Wednesday. If not, I will talk to you whenever I talk to you, but have a good Thanksgiving.
You too.
And talk to you in a couple weeks.
Okay.
All right, Silas. Bye-bye.